All right. So we continue our morning session with the talk by Mohammed Abouzaid. Mohammed.
Okay, before talking, I just want to mention for everyone that there is the concluding conference for the Homological Symmetry collaboration will take place at the Simon Center, Stony Brook, this April 25th to 28th. 25th is Tuesday. The registration is up on the Simon website. You can just go to workshops and find the chronological order to find that. Registration is supposed to close February 28th. Do so if you're interested in coming. As usual, if you are a graduate student or postdoc or a member of the collaboration, you should talk to your BI and funding probably comes from them. Otherwise, there is some funding for participants. Please apply and we can see what we can do. The last thing to say is that this conference is half officially, half unofficially in honor of Tony Ponte. So you should expect that the talks will be a little bit tilted towards the kind of things that they do. So just to have some idea of the flavor of the okay, so now I'll get to the to continue what I was talking about yesterday. So I'll remind you that what I did is I tried to start at the very beginning, very little, and then I arrived at this definition of what I call the using this this, by the way, the notation of and so I'm going to use U2 Milner and decided that we're going to cross these off and use this notation for everything. So this was some kind of ordism of the ride. The ride oracles. Want to call them that. I'd like to call them Cartesian spaces, but I'm losing the battle. But what I didn't do is I didn't talk about the structures, and I did mention that somehow the most important one for us when we were talking before the direct cases, sorry, that should not be capital. That's not the holographic. That should be Roman and Sioux. So this is for stately complex. There are many definitions of this thing. If you're comfortable with, again, orbifolds and vector bundles and orbifolds, then you have a pretty straightforward definition. But I will give the definition that kind of uses the existence of global charts. So this is generated by following kind of data. So you have this T, and last time I used O, but this is really, really horrible name. So I'm gonna go back to this. So what is this? This is manifold. It's a manifold. But it has an action of G. This is compact D. This is a G bundle. Last time I wrote the G acts on it, but I think it's kind of obvious that that's what we should do. And this is a section. And there's one assumption that I forgot to say yesterday, which is that, so one, we want to assume that, and this I didn't forget to say, that it has inverse 0 compact. And two, just the one that I forgot to say, which is that the isotropy, the stabilizers of points that lie in S inverse 0 are finite. So all stabilizers. Along 0 locus. Finite. And it's generated by this modulus of the relation. Which are given by ordism and two stabilizing vector bundle. So you take another vector bundle on E, you replace T on T when you replace T by the total equation. And the last one is I'd like to think that it's taking three portions. And So far, I haven't said anything about this stable complex condition. But it's, if you kind of think about these relations, especially 2 and 3, you realize that there's really only one meaningful notion that you can write down. It's also the one that would arrive, if I think about it, the right orbital. So it's the stable complex structure. Is a, well, isomorphic, stable isomorphism of tangent space of T, direct sum, but actually not direct sum, it's easier to say minus E, and then minus the Lie algebra, G, algebra, with a complex vector, with a, you know, let's say G equivariance with a equivariance complex. These minuses are just there to tell you that this is the virtual, this is the correct virtual dimension, but in practice, because you know E direct sum copy of itself has an obvious almost complex structure, just multiplied by I, and similarly U of itself, you can just replace this direct sum that you didn't know in the definition. Except that you normalize what the word is. So if you don't want to think that that's virtual differences of vector bundles, you can take that. Okay. So that's the definition, and what I mentioned last time was that basically we know very, very little about this group. We know that it has this time. There's a question? Probably not. From the complex cobordism groups, is it derived to this thing, or you just set the vector bundle to be trivial, and the section to be trivial, or the group to be trivial. Okay. And yeah, so so there's some, you know, let me first say, so I have a conjecture that makes this so it's smooth injected. It should be possible to extract from some work in stable homotopy theory some conjectures about how this is, you know, the value at this point is the 3 billion group, but you have to be very careful because their condition, the way that stable homotopy theories have been thinking about this is that their notion of complex cobordism, G-equivariant complex cobordism, does not have this copy of the algebra here. But they tend to, well, of course, they tend to not think that it's the right thing, but in the G-equivariant case, they tend to just assume that the total space is stable complex structure, which is not the same notion. Okay, so we know very little, but one thing we do know is that there are non-trivial, that this is non-trivial. Okay, and there are non-trivial maps from this to other homology. So this is what I'm going to discuss is joint work with Ivan Smith and Martin Klein. And it's you know, some of it is already up on the archive from last year, and some of it will be up hopefully in a month or so. And the first thing we do in the upcoming, so what we did earlier, we did is we showed that n bar 0 and x beta. Okay. We didn't say it in this language, but basically it has a well-defined class of this derived orbital Borsian group as a well-defined class. So this is in derived Borsian group of x to the n, or x to the n. The reason that it lives in there is because you have these evaluation maps. But if you want to be even more precise, you can also evaluate down to the underlying moduli space and give myself a little bit more room. Derived ordering root of x to the n cross n 0 and bar of a point. Okay. So we showed that this is well defined. In the sense that when you change the almost complex structure, you get these relations. And we extracted from this some, we could call them variants. With values in certain homology theory called homological. Well, really something more general, but then just say this today. And I don't want to talk about homological theories today, but I do want to mention that this actually had a kind of a non-trivial application, which took a little bit of work in stable homotopy theory to extract. So we had an application. The application can be stated purely in the world of algebraic geometry, and it said that there's one version. So if x to t1 is a smooth projective morphism, then the complex cobordism of x, which I will write as split additively as the complex cobordism of p1, which is pretty simple to describe. Tensor complex cobordism of the fiber. And this one fiber. This, in fact, does not directly imply the analogous thing for orbital homology with z coefficients, but in fact, if you just play a little bit more with our arguments, you begin to conclude it. You get to conclude the same thing called with arbitrary complex oriented homology theory. What's interesting, this result of this nature has a pretty long history. With rational cohomology, it was proved basically by belief as a consequence of the theory of weights. And the integral question has been kind of mysterious and kind of asked on and off by many people from different perspectives. And it seems to just kind of give a completely symplectic proof. What I want to say is that I'm pretty sure that if this is kind of the origin of this splitting conjecture. If this splitting conjecture holds, then this is kind of almost immediate consequence of the existence of these classes and their variants. And the geometry, there's a little bit of degeneration to the normal cone that goes into this proof of this Barbian theory, the geometry that we use. But proof that we gave really kind of goes through this black box of homology. Okay. So today I want to talk not about this case of not only about this case of genus 0, but also about higher genus. So as I mentioned yesterday, this is already on the archive by another group, Swaminathan and Hershey. They proved that the analogous. Again, they don't quite say that we did, but they proved the analogous like this, whether they proved the analogous results for G1 equal to 0. So the analogous. There is all. But and so therefore, kind of, if you imitate what we did, you pretty easily get again the existence of homological invariance in this. But that's not very that's not very satisfactory, because what you want is you want to understand you want to understand how the Gromov invariants, how they actually relate to each other. You want to know some kind of axioms hold. And without even thinking about hierarchiness, the first question to ask is, can one use these genus zero Gromov invariants to define the deformation of the multiplication to define a version of quantum cohomology? Okay, so that's the subject of this work in progress. And in principle, what I should do is explain to you how to do things with respect to this derived complex coordinate group, and then things will just descend from that. But it turns out that it's actually quite tricky to do so, and we don't yet have we don't know exactly what to tell you in that setting. And so that justifies the idea of trying to understand. So seems hard, or at least so far. Maybe tell somebody has a better understanding to prove the associativity. And it's not so much proving; it's an idea proof is not going to work. To formulate, and you'll see in a second. At the end, by the end of the talk, will be issues the associativity of a quantum derived or doesn't. So instead, what we're going to do is find cohomology theories that live under this, like I was suggesting yesterday, and then try to work in that context. The cohomology theories, generalized cohomology. Under that's Buddhism. And again, if you look in the literature, so far there's one there's kind of not one, there's an infinite family that we describe in this paper with Mark. And so in the 21 paper, used. So now I'm going to give you the full name, and we're not going to talk about it anymore, but we use complex. No. So Borel equivariant complex oriented and local cohomology theories. So this is quite a mouthful. I mean, complex oriented is not too surprising. So they're basically things with respect to which there's atomic and complex vector bundles. Okay. So Borel equivariant means that, well, we're going to have a group G floating around, and we have to figure out how we're going to formulate equivariant, and the answer is you do the Borel construct. That's pretty simple. And so this leaves this part here about whether it needs to be K and local. And this is something which basically requires you to first complete a prime P. So you have to understand how to do homotopy theory with prime P. And then further, at a given prime P, it turns out that MQ splits into pieces, to infinitely many pieces, and then those pieces themselves have some kind of filtration, and then the associated gradient pieces of filtration are called K and Morocco K theories. And then you look at something which was like from the point of view of stable homotopy theory, it is a formal neighborhood of K. And anyway, those are just some words. It's not very, the description is not very. But today, and this is one thing that is going to be in this forthcoming paper, we'll do equivariant, ordinary equivariant K-theory. And I want to spend a little bit of time describing how that works. Because somehow it's much more concrete, and you can have hope of understanding it in relatively short time without delving into just massive statements. Yeah. But forthcoming work. I'll explain what this is. I'll homology. So this is so in fact we should really say a homology theory because I've been sticking with homology throughout. Okay. So it's a little bit difficult to describe KU, so this is K theory. This is something that's called K homology. So it's a little bit, again, K theory is much easier to describe with cohomology theory than homology theory. The cohomology theory is just given by, as I said yesterday, stable complex vector bundles, isomorphism, that's the group. So the usual trick, the fastest trick to define complex K homology is to decide that really you don't care about arbitrary topological spaces. You care maybe just about manifolds. And then certainly for closed manifolds, the trick could be the T-Singer trick. Is to define a lower star of a manifold M. And again, for simplicity, we make it so it's a closed manifold. To be upper star with compact support of, I'm going to write now the normal bundle. And what that means, this is the normal bundle of an embedding inside R K for K very large. And this is some kind of compactly supported K theory. So again, you can define it. So quickly, some degree shifts. And actually, there's very few degree shifts in K theory because things are periodic, so people just suppress them and only keep track of odd versus even. This definition kind of is very efficient. It uses implicitly something called T duality, or spending with duality. It uses the fact that somehow this normal bundle, non-compactification of it and M are somehow dual in the sense of stable homotopy theory, which is basically means they behave like a vector space and it's vector space dual. Okay? And so that means that if you try to define the left-hand side using any other tool, and if your answer was compatible with duality, you get it. Now, this definition looks like it only works with closed manifolds, but actually works more generally because you can find a version of this normal bundle that's going to work for any CW complex. So if you take a finite CW complex, there's something even more general than that, and you embed it in Rn, as long as it embeds it embedded in Rk or K large, then you can have a definition of this nature, which just uses either the complement or something like that to define K. But again, when on manifolds, it's kind of very more concrete because it's normal bundles. Very attractive. Okay. You can do the same thing actually instead of the normal bundle, you can just use the tangent bundles. That is alternate works. Even though it's a little bit harder to justify what's it. So anyway, so this is one way to think about it, and if since we're working with you know, moduli spaces which aren't too far from being manifolds, and then the only other object that's going to appear for us is x to the n times the abstract moduli space of curves, which again not very too far from being manifolds. This is not, you know, you can just use this idea to push things. So I'm not going to construct this, you know, natural transformation. I just want to talk about it today. Scribe. Not on coefficients. So there's this thing where people put lower star here. So you basically need the value of this point. To a. Now K star is very simple. So this is just a copy of Z. Okay. More precisely, it's a copy of Z in each even degree. But there's natural isomorphism between them. So really, it's just a copy. So what that means is that we need to assign to every derived overfold, you know, complex oriented, an integer. And what I'm going to do, I mean, the way I'm going to do it is I'm going to try to do it in such a way that if instead we have a derived overfold over X, which is what happens to homology theory, which means that you have a map, you add 2K X, and so on and so forth, but not quite X, but kind of the dual of X. So anyway, so we'll do it in such a way that if you take what I'm describing and you did it for some derived overfold that is over X, and let's say X was a manifold, then as long as you understand how to do this construction parametrically, which is, you know, some standard thing in index theory, then you can just, you know, it tells you pretty easily how to do the construction intended, the construction kind of homology. We will use using index. Now, if you have, you know, some more homotopy or algebraic background or algebraic background, you think like, wait, you know, like these spectra, blah blah blah. Like, there's just no way to escape this index theory. All the definitions, at the end of the day, all definitions of complex K theory, or rather, maybe definitions of all, and any non-trivial computation involves doing some amount of analysis. What I'm doing is I'm kind of trying to extract all that out and, you know, say something as concrete as possible without a black building block as explicit. So there's a special case. Oh, this not. And that's somehow the beginning of the story. The special case is when you consider a complex manifold. Let's call it. Let me call it. There's too much notation that I haven't. Let's call it complex manifold. I'm going to use this. Okay, so this is going to be in general my notation for a derived overfold. Where's my derived overfold? So i.e. G is trivial, and there is no vector on it. So in that case, this integer that you get is the homomorphic error vector. So as a reminder, so this is minus 1 on the rank homology of X structure sheet, and this is homology in the sense of coherent sheets. And as should be, pretty clear. So the point of this Z here, what's really happening is that this Z is, stable vector bundles on the point, which basically means vector spaces, virtual vector spaces, and so this is really the virtual vector space. So the other thing to say is that this is the cohomology. It's associated to the complex, well, associated to the Doble complex. Functions. So this case is the fundamental case, and everything else requires you to understand three ideas. So I can put them in order, and I'm going to try to put them in the order in which I think they're easiest for people to process. Now we need three generalizations. The first one is you basically allow for a group to enter the story. Soon we have X, which is again given by T with a G action. But then again, go back to one. And now you have to make some choices. I want to stick to the case of being able to write holomorphic things. So the simplest thing is to assume that this has with a holomorphic structure in the directions that are transverse to G. Transverse to G orbits. If you want a different name for this, you can just say that this is a holomorphic one. And in this case, this natural transformation is sometimes goes under the name homology. You have to prove something about this, but you have to construct it first. If you look at how he constructs it, he basically does basically what I'm about to say. So he cites some work of idea that goes back to Tia. And they do exactly the same thing that one does here, okay? Except that instead of looking at one form, you look at one form in the direction which is transverse to the leaves in the orbit. So there is this analog of this local operator. But that's in the transverse direction only. What are the assumptions to G? Compactly. And what I meant to add, so that I have this condition that the stabilizer is finite, I want to impose it again. So actually, this is the interesting thing. So Kawasaki imposes the condition that the stabilizer is finite, and then, because he's thinking about that in this work of Atiyah and Singer, that condition is not assumed. But Atiyah and Singer actually studied this version of K theory, which is called transverse K theory, for compacting group actions on manifolds, let's say, on manifolds, but they do not assume that the stabilizers are finite. They allow some pretty nasty singularities. In particular, they allow having a vector space and a compacting group action on it. And they're perfectly happy to study transverse K theory in that context. The transverse direction. And now the point is that if you try to write down the analogous complex to this, it will not be elliptic. This complex is not.
And that's because of the which complex.
I mean, I didn't quite like it. But take this story here and just imagine putting transverse operators everywhere, only looking at the d-bar operator in this direction. So you're not doing anything in the fiber direction. It's basically like you have a copy of the infinity function from the fiber.
So there's not even like a sheet of section.
But it has a G action. The entire complex of an action has a G action. Okay? And so therefore you can take the G fixed ones. And that is always finite dimension. So this is elliptic. So so we can't really take the rank of the homology.
So if I'm doing this transverse, I have to just take the double complex exactly there.
T is not complex manifold.
Okay.
Okay. So of course you can trade it. You can say, well, actually, this is you can build a complex manifold with an action of the complexification of G. But then, like, G is not compact, and I could prefer it.
What do you do if it's you're not analytic? You have to build something analytic to make this argument.
I will explain. No. I will say I'll say it'll be 3 boards, and then I'll say you take the fiber product of all these 3 things, and that's the solution. It's not that. It's not. But let me finish what I'm saying. This complex is so we can't take of -1 to the I of the rank of HI. Okay, and here I'm going to put analytic with some kind of transverse condition. Not great thing. Maybe. Okay, but it turns out that if you pass to G fixed point, the homologies are the finite dimensional. G next one. G fixed non-difference from G fixed subspaces gives a finite dimension. Gives a basically different elliptic. Yes. It's technically a bad term because ellipticity is some local condition. I should say Fredholm complex. Be better way to say it. But then I have to talk about bounds. So that's the right thing to do. That gives us integer. Now I just want to remark, and we don't use this because we don't currently feel it's useful for. But in fact, Atiyah and Singer do quite a bit more. By the way, it goes back to Atiyah and Singer in 2 separate papers of Atiyah and Singer in which they discuss their collaboration. So this is not the analyst theory. If you know what I'm talking about. There's like, an index of elliptic operators 1 through 5, maybe. And it's not from there, it's from the subsequent. If you want to ask, you can ask me or wait for you to come up with the so remarks with Atiyah and Singer. Study the function irreducible representations of G. Given by taking the pieces of this complex, which in which is given a reducible representation. So in other words, there's a missing statement about the trivial part that actually you can just say, let's break it up into irreducible representation, and then you can given by this by the part of the by the asymptotical pieces. Homology in which is reducible if given by two. And this shows an interesting property that this function. Things don't work. It's not too bad. But anyway, we only need to know this. Okay, so that's part one. So part two is what to do if instead of a G you have a vector bundle. With a holomorphic section. So my picture now is that there's no G because I don't want to talk about it. I just have some T here and I have some D here. I'm not calling it E, I'm going to call it E, and I have the section S. And then the idea basically is that what you want to do is you want to take this homological characteristic, then you want to take this vector bundle and this section into account. Okay? But you don't do it just you don't just do the homological vector bundle by itself. You have to be a little bit more tricky. So you take the exterior algebra on the dual. The direct sum of wedge I of the dual, which is dual. And what you observe basically is this is, of course, this vector bundle on T, but this vector bundle has it actually forms a complex of vector bundle. And the complex of vector bundle is formed by concatenated by not wedging with S, but rather inserting, evaluating against S. Defines a differential. And it makes this into a complex. So at the end of the very end of the complex looks like this. You have trivial bundle, then you have E dual, and then you kind of just pair against S. It's there and then on which two E dual. Yes, you have to. This is the notation for doing things with exterior functions. Okay. So then you do the same thing. You take homological characteristic of this complex of homomorphic vectors. X, and that's pretty cool. Then the definitions, so I'm not repeating, basically do what I said, but I said over there with the definitions. So now comes the last generalization, which is what John asked me about, which is what happens if we don't have analytic structure explosion. And the answer is that basically this was again worked out by T.F. Signer, But that is actually in their MS series. So now what if X is an almost complex number, stably almost. And the answer is that it turned out that you cannot quite write down the low complex, but what you can do is you can equip X with a canonical spin C structure. So spin group is the analog of the spin C group is the analog of the spin group for unitary matrices instead of complex matrices. So instead of the Z mod 2 that shows up when you instead of orthogonal matrices, instead of the Z mod 2 that shows up when you go from SO to spin, you have an S1 extension by S1. And the spin C structures have associated Dirac operator. And then you take the index of the Dirac. Take the index of this. I don't want to go into detail. It's not really worth it. There's plenty of books written about this. Now, really, you just combine these three ideas together. I mean, this is the easiest one. Okay, equivariant. If you have an equivariant spin C structure and compact E group, then whatever it is that I wrote here, whatever it is that is goes with this black box, which you can write down, elliptic operator. Now it turns out you can only write down a transversely elliptic operator, but in the equivariant, whatever it is that this same idea that shows that the G fix. In fact, what the T and single write about is that case, not this case. So it's not that hard. And this takes a little bit more work, but actually, this second part is actually quite easy because it's also in textbooks. There is a proof of the Thom isomorphism theorem for complex vector bundles in K theory, and this is what it uses. It uses spin C Dirac operators because you cannot start by assuming you're not trying to prove the Thom isomorphism theorem for analytic vector bundle from analytic manifold. We're really trying to prove it in context it's very analogous to this. So this is So if you know about this story, if you know about any of these three pieces, if you know about all these three pieces, it should be pretty clear that they all combine together. If you know about any of them, one of them, it should not be too scary to combine with the other one. So great. So this is what. So if you combine all these, if you combine all of them, you get this statement that that's a complex coordinate. So from this we get. We get K theoretic homological. And of course, that's kind of, we didn't invent the subject, so we can write insymplectic topology, symplectic context. And this was done much earlier, done in algebraic setting. By given column. And then now, given the difficulty of comparing symplectic and algebraic Gromov-Witten invariants, in ordinary cohomology, I'm not going to make any claims that that are things you cover. There are things that there is now a new proof of the agreement of these invariants by Swaminathan, even though he hasn't written it up yet, right? Okay, good. I'm looking at his advisor, former advisor, so maybe somebody should try to pressure him to do it. But I would hope that that proof, which, as far as I understand, can now be simplified using the methods that I'm describing, where you kind of just construct the moduli spaces and describe the moduli spaces as these kind of orbifolds. So I'm hoping that those methods can also be applied in the setting to get an agreement that's little. Okay, but this is actually the beginning of the story, because it turns out, and this was really given Tull's observation, it turns out that defining Gromov invariants is not the point. Okay, so these naive Gromov invariants not satisfy any reasonable axis. Well, let me just take the expected axis. In particular, let me do the first one. So I'm going to assume, so M is going to be a closed cyclic manifold for me and for him. Right? M is closed cyclic manifold. Then we're saying that you can construct a map, the K theory, and answer K theory of M to K theory of M. From, let me stick to the simplest case, moduli space of points. So I'm going to write 0 and 1. So n is the genus, 0 is the genus, n is the number of couples. 2, 1. So 2 is the number of inputs, and 1 is an output. And this is kind of relevant to this theory because we really do have to break. And as always, what you can do is you can then try to add up all these contributions and maybe use the area of beta, or if you can maybe first homology of n as your coefficients. You can combine these to get a single product. Combine these. Over either Novikov ring or completion of the group ring of H1. Which to zero energy is the classical coupling. And now the problem is that this is not associated. And the reason it is not associative is very simple. It's a geometric phenomenon. The geometric phenomenon, unfortunately, for which we don't have very good geometric solution in complete generality. So the geometric phenomenon has to do with the fact that I'm going to describe this in the simplest case and then talk about things in general. So it has to do with the fact that, well, let's take M bar one. So this is this moduli space, which normally would appear in a proof of associativity. And it has a map to n bar 0, 4, okay, which is key. So now in here, you have just points corresponding to, I'm just going to just draw it as a class on this curve. Let's say this is 1, 2, 3. And then you have another class of the other. And it's pretty easy to arrange to have a diagram of this, where this here is, well, it's a little bit, complicated. Maybe I shouldn't put here beta, here, a little bit of beta here. And then it's this joint union over beta 1 plus beta 2 equals beta of this beta 0 to 1 x beta 1 cross 1 beta 2. And you have a similar thing on the other side. Okay. So the issue is that this map here, and this is again, this is not our point. Given top, we like this problem. And go. This is not an embedding. Instead, it's not an embedding. So there is the actual inverse image in here, the actual fiber. Fiber is some kind of normal crossing of fiber. So what you want to hope, so if you want to prove this associativity, the way you want to do this is you want the most algebraic way to do it is to say, oh well, all I want to do is I want to take, this fundamental class of this, and here there's take the homology of this, or K-theory of this, there's a class associated to this point. First chunk class go over 1 on P1 basically. You pull back, you cap against the fundamental class of this, and you would like for that to be the image of the fundamental class. And that's just not true. You can see that it's not true in some very simple case, which is just if you consider the nodal degeneration of an elliptic curve. Sorry. Nodal degeneration of an elliptic curve. And you could ask yourself, for example, how can I describe the K-theory class? Under this kind of tall map of the elliptic curve in terms of the 1 to P1. And the point is that the elliptic curve is actually 0 in the complex covariance group, because the complex covariance group is basically detected by the first term. So it cannot be, so you cannot have a formula for this general fiber, which is what you would get if you said, oh, I'm going to take first term class of this line, whatever the class associated with the divisor, pull back in the intersection. You wouldn't. So you would get the answer from the general fiber. You cannot express that in terms of the normalization of the singular fiber, which is basically what this is. This is what the normalization is. What you need is some additional information that is hiding here. So if it was the case that this normal quantum divisor was in some sense arbitrary, then we would lose all hope. And there would be no way of correcting this picture to get something. But given Toll's observation again, the next thing you're going to say is going to seem everything here is going to seem tautologous. The whole point is that he managed to see through the whole sequence of arguments from the beginning that something is not associative to the end, that you can actually correct it to be associative. The point is that the non-trivial strata of this normal crossing divisor strata this fiber over this point, fiber over the second point in P1. And 0 R. Okay, so let me, so what it means is in K-theory, for example, you can just write down an equation for what this class of this fiber is, which is the thing that's going to be invariant and is going to allow you to move from this fiber to the other fiber and run WDVD, whatever the argument is. Okay, and you can just explicitly describe it in some sort of by some inclusion-exclusion formula. You basically take the whole multipolar characteristic of the strata indexed by the codimension, -1 to the I times. It's a very special case. It only works for K-theory. There is a version of it in generalized homology theory and other homology theories, which I'm trying to have time to get to. Do I have to stop? Yes. I'm going to have to get to it. So certainly not going to get to it. It's describable as follows. And now, given Todd's point is, what you can do is you can decide how you're going to split this curve. Okay? You can decide to either split it like this, in which case you decide that all the contributions that are contributions that you were not expecting to see from the point of view of ordinary homology, because they come from higher dimension strata, you will assign all these contributions to this first one. So this allows you to give you so this gives a correction to fundamental class of n n0 to 1 at theta. And now for which associativity. So that's given somehow the nature, the geometric nature of this normal crossing divisor is such that you can incorporate terms which you don't want from a certain perspective in the contribution of the input, and then write it. Now you could do the opposite thing. You could decide, oh, I'm gonna assign this to the output, okay, and then write it in terms of the output. But the one thing that I want to say is that, as far as I know, there is no way to do this without breaking symmetry. So the thing that we're used to from ordinary homology, where there's inputs and outputs, and it doesn't really matter because there is pairing. Here, there is some way of building a corrected pairing. It's not clear that the pairing is symmetric. It's not clear how to formulate things in that language. But the last thing I will say, just before I'll continue the afternoon, is that one of the things we do in this paper with Ivan and Mark that's coming up is that we can extend the story to again this word rel variant kn local complex oriented homology theories. And when I say extend the story, I don't mean that K-theory is a special case, because it is not. K-theory is different because K-theory is not Borel covariant. used. So in some sense, there's really currently there's two pictures. There's this sporadic covariance theory, this genuine K-theory story. And for both of them, we produce things like associated product, associated product. In the sum sense, what we do is we take all the operations, we assemble them as operations with only one input, one output, for the N1 X data. Okay. These are the moduli cases. We consider we always have at least one output. I can also maybe I'll also have at least one input. I have to check. And we say that this forms some structure, that this structure is like an algebra over, they give you an algebra over the apparatus of the functions. Okay, so I'm going to stop here and continue that.
Thank you very much. Question?
Yeah. To define the map from the derived alternative what is the K homology is the only way use analytic. It described using the index theory to define this map.
Yes.
So are there purely topological ways to define?
The way that I would there can be no purely topological way because the proof of what periodicity uses for a method analysis. So the question is, what is the minimum analysis that you need to do so? I really think it's really going to be well. Here's what I can say. The homotopy theorists have incorporated a lot of this analysis in the statement that K theory forms a global cohomology theory, which means something of the form, all equivariant K theories assembled together satisfy a certain set of actions. The proof of that uses a lot of analysis. So if you just take that as a black box, you come pretty close to proving everything that I'm not completely sure because they haven't proved these transfer maps. So I think they actually didn't build the black box sufficiently well to prove the existence of wrong-way maps. All the wrong-way maps are real. So I think it's still the case that you have to kind of go back and figure into the analysis.
Other questions? If not, let's thank Mohammed again.